Alright, welcome back everyone to another video, and in this one I thought I would go in more depth about the PCB design that you see here. Stuff which I couldn't cover in my previous video since it would have gone on for way too long, so I thought I would have rant and explain everything in this video. Feel free just to put some headphones on and listen to this whilst I talk about all the previous design iterations we've had here for this board and my logic behind doing design changes into each one, as well as all the component placements and stuff like that. You are more than welcome just to listen to this in the background, because I think it might make a nice listen to. Anyway, so I think for this board we should probably start at the first board that I made. So this here is the first board that I came up with. So I'm just trying to reach behind me to get something. And this here, so essentially what I did first, before I did anything, was I took my 722.6 TCM out, and I measured up the board to work out where all the holes are, where the mount holes are here for the TCM connector. And then I drew my footprint out in EasyEDA with that. So that was my constraints, was that it has to be within the same TCM board. Now, on here you'll notice that it's a TNC4 we are using. That's because it is the fastest MCU ever built. And the circuitry on here was pretty much a copy-paste from the 722.6 control project, which I'll quickly throw a link up on screen now. The original designs for this were designed to be a standalone controller, the 722.6 control one, and I just thought I could copy and paste the circuitry onto this board. Turns out that wasn't correct, and this was ages ago, I believe I did this. I think I did this over a year ago. So yeah, this would have been when my electrical design skills were like in their infancy. And yeah, there's loads of stuff that I've done wrong here looking back a bit. Component placements here, the trace widths for this pin over here are completely incorrect for power, because I'm basically giving no power to the solenoids, which would draw like 6 amps. These are meant to be octocouplers again, and then these are the MOSFETs. So these basically drive these MOSFETs here, and you can see the diode directions here. And then on the back of these boards, you can see these absolutely ginormous trace widths, ginormous traces going all the way to the other end of the board. Again, not optimal. And yeah, there's this giant plus 12 volt rail at the back, which yeah, again, is not really great. So that then led to iteration number 2, where I completely ditched all of these octocoupler and MOSFET driver setups in favor for some solenoid driver ICs using the TNC4. These are the TLE6220GP. Again, I'll throw the datasheet up on screen probably. And I'm sure you are wondering what all of this stuff down here is for. This, oh, come on camera, focus. Thank you. Oh, you didn't want to focus. Come on, you can do it. Focus, please. Thank you. So, since the TNC4 can only handle 3.3 volt I/O, and these TLE6220GP chips can handle only 5 volt I/O, I'll quickly throw up from, I can't remember exactly which board it was that these circuit designs came from, but essentially this is a bidirectional logic converter, and I have one of these for each one of the pins on either one of these solenoid controller chips, and essentially each one of these can drive 4. I believe these were designed for injectors, but anyway, each one of these can handle 4 channels. So I have 3 on here handling the shift solenoids, and 3 on this one handling the pressure solenoids, like shift pressure, modulating pressure, torque converter pressure. Then on here was my first attempt at changing the power delivery system to a buck converter, the which one was it? One second. LM25765 chips. And then this was coming to look at it. I basically looked at the reference design for the circuitries for these to work out where the capacitors, well, but I needed the capacitors, I needed this, I can't remember the exact name of this. I've got one of them on my new boards here. I cannot remember for the life of me the name of this component, but anyway. Again, I'm not an electrical engineer. And diode placement. However, looking back at this again, this is a really suboptimal board with the way it's been designed. Again, mad traces on the back, and there's just like not really anything safe about this board. So I ditched that. And then on one of my streams about 6 months ago, I assembled revision number 3, which was my first board to kind of work for testing purposes. So this was the penultimate one I did on the TNC. So again, we've got a TNC4, we've got linear voltage regulators because I gave up on the 25765 chips because they weren't working originally. We'll get to why that is in a minute. But I ditched them for something simpler, which is a linear voltage regulator, so one for 5 volt and one for 3.3 volt. If you're looking at this wire here, turns out the 3.3 volt, as to what this does, turns out when I designed this, the 3.3 volt regulator cannot provide enough current to power the Tinsy, but the 5 volt can, so I just ran a wire directly from the output of this to the plus 5 volt rail on the Tinsy. And then the Tinsy's onboard converter converts that down to 3.3 volts for the chip. Then on here we have our sensors and our TLE6220GP chips. Now, if you're wondering why I gave up on this one, and again here you can see my bidirectional logic converter. So notice on this one how they're more spaced out than on this one. That was purely because back when I did this board, I had no means to hot air solder. So when this board came through and I looked at it, I said, hang on a minute, I'm not going to be able to solder any of these individual like resistors and gates here. So I decided to space them out a bit more on here. Again, bad mistake, because it turns out with all of this malarkey going on here and all my weird pin placements here and all of these giant like 2 amp rails going up and above all the logic lines, turns out SPI doesn't work on this because it's getting so much interference between here. Again, when I designed this, I did not have an oscilloscope, I just had a regular multimeter, so I had no way of actually checking that. The capacitor placements down here are just purely due to down to the reference design for these chips. It basically states how far away to put them, so I started following the reference designs for these. So, now leading on to revision number 4, which you guys never saw. So I decided to ditch the 6220GP chips, because these are only basic, so you basically just give it a PWM signal and it will output a PWM signal to a solenoid. That's all that these things do, and over SPI, the diagnostic features of these chips are purely to detect if it's overcurrent, there's overcurrent, undercurrent, short, or overheating. That's all that you could do for this. So I then found the TLE, one sec, I'm going to quickly get the name of the chip up because I remember I had so much pain with this. Okay, TLE824533SA is what these are meant to be. And this was during the height of a silicon shortage that I decided to buy these. So naturally, I couldn't find them anywhere, so we had to park this board and never come to it again. But again, I started following the reference designs for where to put all these capacitors, how to hook up everything. Again, these only ran on 5 volts, whereas the Tinsy can only handle 3.3 volt logic. So I decided to, instead of using all of these messy circuits, I decided to actually use a bidirectional logic converter IC. So that's what U6 and U7 are on this board. And again, we're sticking to the rest of the board is identical to the previous iteration. It's just the different chips. And I wonder if I did some changes on the back. Yes, the back definitely looks a bit neater. So you can see on this one versus the traces on the back here from the solenoids, way neater. So then I took a break from after we designed this board. I took a long break of about 2-3 months because I was working on my open vehicle diagnostics project, my thesis, and a bunch of other uni stuff. And then come summer, I decided to ditch the Tinsy 4 because I also did some testing with it back on this board here. And it turns out it can run free real-time OS on here, which is basically a way of having like threads and stuff all on the same CPU core, much better than the standard Arduino code. Except if you enable it, you then start screwing around with the timers on the chip, which then affects the PWM signal pins. So I just said it's not worth it. This chip with the Arduino IDE doesn't natively support what I want. So I threw the Tinsy 4 out. And this was the last one to feature it. But again, I was testing this after I built this board and realized I couldn't get the components for it. So then that leads me to revision number 5, which was the first one we used. I used the ESP32 on. Now, if you noticed on here, there's a huge design change. So I basically deleted everything and started again on this board. I said, I'm going to start fresh. So we're using an ESP32 because that supports FreeRTOS, and it's a dual-core 240 megahertz CPU, so very nice for processing. And I was like, you know what? I've had experience with the ESP32 thanks to, one second, let me unplug in, the Machina A0, and I found programming that was very nice, so I decided to go ahead and use the ESP32. as you will probably notice, I'm using the LM25675s again here. Now, this is because on the original board that I had used them on, one second, let me find it, here, turns out I was using the reference design for like the schematics to kind of say what should be connected to what, but I wasn't using the reference design for component placement, which meant that I was getting too much noise on these circuits and it was just kind of failing to do what it was supposed to do. So on this board, I actually followed that design, and you can see also the trace whips leading up to it are way fatter. You've got these actual sections of copper, which again is according to the reference design of that. And then on here, I have capacitors up here now. These are for ESD protection on each one of the solenoids. And then this little chappy over here will bite me, but we'll get back to that later. As for the design of these circuits here, so I've ditched the driver IC since I basically couldn't find any of these anymore online, and went with a more traditional circuit whereby we would have a MOSFET and a diode, and the Arduino ESP32 will directly drive the gate of the MOSFET. Since these are logic level MOSFETs, they can run on like 1 to 2 volt gate threshold, so 3.3 volts from ESP32 is more than enough to drive these. These are R24, R23, R6, etc. These are, I believe, these are 120k resistors that I put there to ensure that when the ESP32 is turning on and hasn't configured any GPIO pins, that the gates of these remain shut, meaning that the solenoids don't accidentally turn on whilst the system is powering up. Now, if you're wondering about the actual design of this circuit itself, this comes from the EGS53 ECU. So one second whilst I get that. Okay, we are back. So this is EGS53, which is the 722.6 controller from 2008 and plus, and newer. And I essentially reverse engineered the circuitry behind these two solenoids only down here, which is MPC and SPC, so modulating pressure and shift pressure. So you have a MOSFET here with a diode going back out to the positive rail for the solenoids. And then you also have a current sense resistor. So I essentially copied this layout over here. So here you have your power coming in through this little side trace. You've got a diode bringing it back down to the positive rail S power up there. And then you have a current sense resistor leading to the gate of the MOSFET. Not gate, sorry, drain. Or is it source? I need to look at my schematics. Anyway, I'm, again, not an electrical engineer here. I'm just saying what I was doing. And I needed a way to measure this voltage drop along here. So on the EGS53 board, I couldn't actually work out how it was measuring the voltage drop, since this is like a 4 to 5 layer PCB, so I couldn't trace it properly. So I ended up doing some looking online. I found a chip called an INA180, which does exactly what I want it to do. So I placed one of them next to the current sense resistor, which is basically a 0.005, I think 5 milliohm resistor, just to calculate the voltage drop. And I specifically chose the A3 variant of the INA180 because it has the correct gain level, so that the ESP32 can directly read from this without it even. So I believe with my gain, with the A3 model, 0 volts would be 0 amps, and 3.3 volts or 3 volts, which is what the maximum the ESP32 can detect safely, would register 6 amps. Now, these solenoids on the gearbox should only draw at a maximum 2.5 amps, so that's a good safety margin. If I see anything near like the 4 to 5 amp range, the controller, I will code the controller just to shut off the solenoid circuit because there's a short somewhere. Then also for serial communication to the ESP32, I was again looking at my existing designs here from the Markinet A0, and in fact they have their schematics open sourced and online. I'll quickly throw it up on screen now. And I essentially kind of copied their circuits here, except I didn't want to use the CP2104 chip, which they used for USB to UART communication, because it is so damn expensive compared to using something like a CH341. However, I did try assembling this board on screen, and it didn't work. We could not get the serial communication to work. So that then led me to my next iteration of the board, which is this one here, where I kind of just threw away this chip and sucked it up and went with a CP2104 over here. And again, you can see some components have changed. So we've now got a 3.3 volt regulator here. So that was also one thing about this board that I had forgotten. So when I plug this into power, without plugging it into the gearbox, or without plugging it into the car and powering up the car, there is no way for the ESP32 to get power if you just plug it into the USB port. So I solved that in the next iteration by adding a 3.3 volt regulator over here, so that it can just power the ESP32 so that we can program it on a desk with just a USB connection. I also switched from using a USB micro B port to using a USB Type-C port because I did get a lot of complaints about that. People asking me, oh, why aren't you using USB-C? It's so modern, like why are you using old school stuff? So again, yeah, I moved on to that. And again, basically nothing else changed on this board other than just the serial communication. Now back to this guy over here. So this guy bit me, and my original intention was to have a global enable for all the solenoid power. And if any of you watched my stream when I assembled this blue board, I hooked up this particular MOSFET here and didn't realize it was a high side. It was meant to be for high side, not low side operation, it's meant to be for low side, but I had it in the high side operation mode, which ended up meaning that I accidentally, when I powered this on, sent 12 volts directly to the ESP32, frying it. And in the end, I just decided, actually, I probably don't need that. So in the penultimate revision of this board, we removed this, which brings me to my black board, which you've probably seen on Twitter or whatnot. Follow me, by the way, if you haven't. Where we have done some very minor changes. So as you can see, the bottom of the board looks basically the same. So does the sides. Just the only thing different really is the top, and I've added these giant capacitors in here. These are just to purely provide some extra buffer for when the solenoids first turn on during their PWM sequence, so they don't immediately start drawing from the car's power supply, which causes huge fluctuations in voltage. So I've noticed that 3 of them was a bit too much, so you'll see in the purple board I have over here that I only have 2 of them rather than 3. Because this was just for testing. I didn't know how many I'd actually need, but yeah, it helped. Then, yeah, that was about the only change on these boards, other than some, let's have a look at the back. Yeah, other than some minor changes, like the trace whips got improved a bit, I improved the grounding layer a bit, just some basic stuff. And then that leads me to my final assembled board. Oh, also, when I did test this, because this was the first board I actually plugged into my car to test with, we had trouble with the N2 and N3 speed sensor readings. They're meant to be Hall effect speed sensors, according to all the documentation. But it turns out these work in the opposite way to a Hall effect speed sensor, in the sense that these pull down a supply current rather than producing a pulse of a supply current. So that kind of didn't work with these boards, and I actually have an image of when I played with the board to get it to work. So I basically had soldered some resistors onto 10k resistors for pull-up, and I just brought 3.3 volts to those 10k resistors. But then, yeah, that proved to work. So then I took that and wrote the final design, which, as you can see, now has these pull-up resistors here. So basically you get 3.3 volts going up to here, with some capacitors just for smoothing the signal so that there's no huge... because I've noticed that especially with when the solenoids are turning on, there's loads of noise on the sensor pins, which then means the ESP32 can't correctly count the number of pulses. So there's, for the N2 and N3 speed sensors, there's 60 pulses per revolution of the input shaft of the gearbox. So again, this was just purely, the capacitors here are just to smooth out that signal a bit. In fact, I think I've got an image. Yeah, I do have an image of what that looks like before and after I put the capacitors in. But other than that, there is literally nothing different about this board, other than some minor component placement changes just to make things a little more compact on the board, which helps to eliminate some noise. Oh, I also added these 100 nanofarad capacitors here because it turns out in the INA 180 specification it states to have these very close to here to eliminate noise, which it did do. So that was just something I was missing from my previous iteration board. And then again on the back we have just updated the trace width. So that was again another thing. The trace widths on here were, I think, 40 mils going up to so these fat ones here are about 40 mil width. Turns out that gets very hot when trying to send 2.5 amps through it. So these ones are now 80mm, which is substantially thicker, and it doesn't get nearly as hot as the previous one. For those wondering, I am using 1 ounce copper rather than 2 ounce copper on these ones. So that basically means I have to make my trace widths wider to compensate. Also, one very minor design change is the width of the pads to connect the TCM connector to have grown substantially, as you can see from these little circle ones to these oval ones here, and that's just to overall increase the strength of the connector so that I don't accidentally break the board if there's like stress applied to it. That's all that really does. So yeah, that basically covers everything, I think, about all the design changes that we've and board iterations that we've gone through. I mean, again, I'd like to reiterate, by no means am I an electrical engineer here, but this has kind of been my journey as to designing the PCBs and kind of getting to somewhere where things work, and I'm happy with it. So yeah, just thought I'd upload. Oh, also, before I forget, one other design change. If you look over here, I completely removed this piece of the PCB because it turns out that the substrate that the PCBs are made from is a perfect signal jammer for the ESP32's antenna. So just removing this chunk out here seems to substantially help with signal quality. So I can actually now communicate to the ESP32 in my car whilst it's in its stock TCM position behind all the carpets. I can now talk to it via my Android phone, which is great for some of the future stuff I'll be doing with this. But yeah, stay tuned for all of that, and I hope you all have a good day. I'll see everyone in part 2 of this series. But yeah, just thought I'd quickly upload this video just explaining everything that I've been doing. So, goodbye.